We have two teams that are going to be presenting this morning, small unmanned air systems that they've designed over the last semester. Before I introduce the first team, I'd like to introduce our panelists. Actually, I'll let them introduce themselves.
Steve Jacobson. I work at NASA Armstrong at Edwards Air Force Base, and I'm the branch chief for the Controls and Dynamics branch.
Ed Burnett. I'm a senior fellow at Lockheed Martin Skunk Works, and I'm currently the X-56 program manager.
I'm AJ Olson with Sierra Nevada Corporation out of Denver, Colorado. I'm one of our lead engineers on one of our largest main ISR platforms.
Okay, thank you guys for helping us out. All right, so I'm going to turn it over to Claire Klausner now. She's going to introduce Iluvatar Aerosystems.
Good morning. We are Iluvatar Aerosystems, and I'm the team lead, Claire Klausner. Today we'll be going over our final design review. So here's our brief overview. We'll be going over the team introductions and then the mission requirements, and then we'll go over individual sections, and then I'll go over project management and some conclusions and recommendations in the team. So for the team, we have Peter Davidson, Paul Kim, Joshua Parr, Mark Tversky, Andrew Wilson, Joshua Day, Christopher Sutton, Morgan Conklin, and Christine O'Keefe. So here is our design process overview. So at the beginning of the semester, we had our design concept review, which was our initial design envelope, as well as selecting airfoil and aircraft sizing. And we moved on to preliminary design, which included theoretical aircraft performance, and then iterating those dimensions of our design. And now we're moving on to the wind tunnel test plan. And this is where we will be doing our representative aircraft performance, and then on model assembly. And the next semester, in detail design, will be wind tunnel testing our model. So here's our mission requirements. We are tasked by the U.S. Department of Transportation to create a small unmanned aerial system that will be able to survey and track traffic. We'll be able to recognize a vehicle and identify a license plate being 6 inches by 12 inches, and then perform traffic surveillance missions of 3 hours. This will be assembly from transport container of a 3 foot by 3 foot by 6 foot box. And then we'll have a launch to climb at altitude of 1,000 feet AGL. These were given by Professor Helbling in the request proposal. Using the RFQ there. So here are some drive requirements. We are semi-autonomous. We'll be autonomous during cruise and loiter, and then we'll be remote piloted for takeoff and landing. We'll return to base if communications are lost, and then we're usable in light wind and average weather, and then modular components will be allowed for easy assembly on station. Here's a preview of our initial design. So you can see we have an inverted detail, and then we have our pusher prop, and then our payload up here in the front. Our payload drives our mission. And then here's our most current design. We added our ailerons, and then we have our inverted detail with our rudder baiters. Still the prop is a pusher, and then we actually lifted up the engine so we would eliminate prop strike. And we did a cone lift. So here is a drawing. We are just over 7 feet, with a wingspan of just under 15 feet, and then a height of 2 feet, just under 3 feet. So here's a CAD rendering by Joshua Parr of our aircraft. And then here's a similar aircraft. So the Penguin VE has a similar inverted detail, and it's also electronic. We have a full electronic aircraft. And then the Raven is also a pusher prop, and then the Silent Falcon has a similar payload, similar missions. So here's our mission profile. This will be gone over in more detail in the acceptance performance section. But you see we have our takeoff and then our climb, and then we'll do cruise and loiter, and then descent and then landing. Here are requirements. So here on the left are given by the RFP, and then where we are today. And we'll be going over these in more detail in each individual section. And so now I'll hand it off to Peter Davidson for payload systems.
So today I'll be covering the payload systems. As an overview, I'll be going over our sensor capabilities as well as the gimbal capabilities of the payload. So you can see here a photo of our payload, enabled with the Silent Falcon Vision camera system. This is pre-assembled from the manufacturer. And as Claire mentioned, the payload drives the mission. This is what allows us to accomplish the identification and recognition mission of vehicles and license plates. So you can see, on the image, there's an electro-optical camera as well as an infrared camera. The electro-optical camera can be any Sony Block EO camera, and then the infrared camera is going to be a TAL2 forward-looking infrared system. The electro-optical will be used for daytime identification of license plate, and the infrared camera will be used for nighttime recognition of a vehicle. So with that, we have to establish a required field of view, and with that we have the resolutions of our electro-optical system as well as our infrared system. As you can see, the resolutions on the screen right there. As Claire mentioned, the target sizes, we have to be able to identify a license plate and recognize an average car. Identification means we can make out specific details on that object. Recognize just means we can see what that object is, differentiate between a car and a horse, for example. So using this graphic right here, this will explain some stuff I'll talk about later, but you can see this is our field of view. That is what the camera is currently looking at, and this larger cone right here, that is the field of regard. That is the total area of which the camera can see. Also, you see this image up right here. This comes with our spot widths and spot lengths. That's basically the projected area on the ground that the camera is able to look at. That will become important when we're going over our mission performance and analyzing how much ground time or how much area on the ground we can cover and be able to cover our mission at. So these are our calculated numbers we got for our required field of views, as well as our swap widths and swap lengths. And you can see these were accomplished with a look-down angle of the payload at 30 degrees. So take our wind tunnel model here. That means our payload is looking down at 30 degrees, and it's able to accomplish that mission right there. So the payload is on a stable gimbal turret, and so it's able to lock onto a target and be able to track it using built-in software that comes with the payload device. It only weighs 2.86 pounds, and it's able to go to -90 to positive 150 degrees tilt, so it means it's able to look straight down, and it's able to turn in on itself and able to protect itself if you want to be able to do a visual landing, protect the camera lens if you're going to land on a not optimal surface. Also, it has a continuous pan capability, so it can rotate full 160 degrees to get that large azimuth, which is going to make our field of regard nice and large, which is what I'll be covering next. So the field of regard, as I mentioned, is what the camera can see. So what this graphic right here is an forward-looking aft projection of any blockage caused by components of the aircraft itself. So you can see our nose gear blockage and our wing body blockage are large components, and our design is going to be, or our field of regard is going to be driven by the nose gear blockage. So there, if you take our wind tunnel model here, there's going to be a nose gear right behind the payload right there. And that is going to be limiting our field of regard from about -150 to positive 150 degrees. And then anywhere other than that, you should be able to see, you will be able to see any payload that is on the ground. So any target that's on the ground. So we have a large field of regard to accomplish the mission. So in summary, I went over the sensor capabilities as well as the gimbal capabilities. We were able to meet our mission requirements with your calculated field of views. And we have a large field of regard, and our gimbal turret is stabilized, allow us to be able to identify the license plate or recognize that vehicle. Next up, Paul Kim will come up and talk about the communication systems.
So today I'll be talking about the data communication link, the transmitter antenna, the data input instruments, and the environmental interferences. So this is the basic system layout of our communication system. As you can see, the payload will be functioning on a different frequency than the flight control system, and this is due to reduce the interferences that may occur between each frequency. So using the vertical pixel density defined by the Peters-Davidson's payload section, the framing was calculated to be 5.23 frames per second. Now using this equation, we moved on to calculating the image data rate, which is calculated to be 100 megabits per second, and that gives us the first platform to discover what bandwidth is required for this mission. And the signal to noise ratio is also calculated using the specifications of our ground antenna, as well as download assumptions, and it was calculated to be 11.0 decibels. Using that signal to noise ratio, the bandwidth was converted into megabits per second, and as you can see, the 2.4 gigahertz and 5.8 gigahertz can handle the 100 megabits per second calculated earlier in the slide. So this is a range equation given by the gun lock text. Using the ground antenna specification and gun lock assumptions, the range was calculated to be 22.1 nautical miles. The RFP requirements state that the range needed to be 10 nautical miles, and we are predicted to meet, according to our communication system, with 22.1 nautical mile range. This is a transmitter that we'll be implementing to our comm system. The emergent RC audio video transmitter. Key thing to know is that the frequency is a 2.4 and 5.8 gigahertz frequency, and this can be changed using software installations. This is the ultra slim peel and stick antenna. Our fuselage is made out of the non-metallic E-glass, and again, this can be functioning on the 2.4 and 5.8 gigahertz, and it can adhere to a non-metallic surface. So this was designed for our sting. This is the pedostatic sensor that will be implemented into the sting. This is the UAV factory pedostatic tube. This is also used in the Penguin BE UAS. And it has a 5-hole probe, which gives us angle of attack, side slip, in addition to airspeed. Talking about environmental interference, there's two types, the electromagnetic and the radio frequency interference. And in order to compensate for these kind of interferences, physical separation was implemented using Austin-Trumbull radio boxes, which will help with shock and vibration absorption. And all the cabling running through the communication system will be shielded properly to help with the interference. This is a layout of our component diagram. This is the payload that will be connected to a transmitter on the 5.8 frequency, which will then come outside the fuselage into a peel and stick antenna. On the other side, the autopilot will be connected to the transmitter, which then again will be connected to the peel and stick antenna on the outside of the fuselage. We place the fuselage on the bottom portion of the fuselage that will help with any interference that may occur during banking in the mission. So in summary, the payload runs on two separate frequencies, the 2.4 gigahertz and the 5.8 gigahertz, and the RFP requirement of 10 nautical mile range is predicted to be met with the 22.1 nautical mile capability of our communication system. And next, I'll hand it off to Joshua Parr to talk about the initial design envelope.
Thank you, Paul. So, brief overview of initial design envelope. Wing and power loading, also be covering flight constraints, initial design envelope and values. And it's important to note these are the starting values for our conceptual design phase. So that should be reevaluated, and with our prelim design phase, those will be covered in later sections. So wing loading is weight divided by the planform area. It determines the initial planform area for our wing. Then power loading is the weight divided by power. It determines the initial engine power, which really goes into our engine selection. And all these are going to be determined by the flight constraints. So the flight constraints are shown here. The important ones to note are stall speed, takeoff distance, and our 2.5 G maneuver requirement, because they're actually going to determine our design envelope space. And these equations come from Roscoe and Raymer are in terms of wing loading and power loading. So this table here shows important initial values. Now the really important ones to note are the air density at 6,000 feet MSL on a hot day. So that hot day condition is a standard atmospheric hot day condition, plus 44 degrees Fahrenheit at sea level. Then another important value to note is our maximum coefficient of lift, which is 1.34. That'll be covered later in the aerodynamics session by Mark Dvorsky. And then you have our aspect ratio of 14, which will be reevaluated again in the aerodynamics section by Mark Dvorsky. And then you have our span-wise efficiency, which is assumed to be at 0.8. But once again, that was reevaluated technically later on. And it was updated. Moving on, using those values with the equations I mentioned earlier, we were able to then plot the values in terms of wing loading and power loading. That gives us our initial design envelope. Now, it's important to note that we have the dotted gray line, which is our stall speed, and then you have our 2.5 G maneuver requirement, which is the green line, and then you have the yellow line, which is our takeoff distance. And that determines our design envelope space. Now, if we decided to maximize wing loading, that gives a value of about 2.05. And then at that 2.05 value, we had a maximum power loading of 27.12. Then we added a 5% margin of growth factor to that to get our initial design plan, which is shown here. So when we applied that 5% margin of growth, we got our design values. And our design values were wing loading of 1.95 pounds per foot squared, and then power loading of 25.8 pounds per horsepower. Now, assuming a max weight of 30 pounds, we have a required platform area of 15.4 feet squared, and our power required 1.16 horsepower. In summary, we are initially predicted to meet the following requirements that I covered earlier. if we have that required planform area and that power required. But like I said, these are actually going to be reevaluated and covered in later sections, with the wing planform area being covered later by Mark Jaworski and the aerodynamic section, and the power required being reevaluated by Andy Wilson in the power required analysis section. Now I'm going to hand it off to Mark Jaworski to cover aerodynamics.
Thanks, Josh. So I'll be talking about the aerodynamics analysis of our state design. So the values that I used were iterated from the conceptual design, in that our span efficiency was reevaluated as well as our aspect ratio. I'll also be talking about the drag, which is consisted of the parasitic drag, induced drag, trim drag, and cooling drag. And these will be used to find the lift-to-drag ratio and endurance parameters used in the power requirements analysis to evaluate our RFP needs. So the airfoil we selected based on evaluation of maximum CL max and stall speed or stall angle of attack was the FW67. We also evaluated aspect ratios from 12 to 18 and chose 14 based on those parameters, as well as not making it too large to make sure the wings weren't too long and skinny and reducing structural integrity. We also had the platform area discussed by Joshua Park, and our span efficiency was reevaluated to 0.93 using an equation from Grant's textbook, and our mean aerodynamic chord turned out to be 1.05 using the aspect ratio and platform area. Next, I'll talk to you about the drag. Parasitic drag is found using a component drag buildup from Raymer, and it used the form factors and the interference factors, as well as the skin friction of each component, along with a leakage and perturbance drag and a miscellaneous drag term. And this turned out to be 0.0267 compared to our initial estimate of 0.02. The induced drag is proportional to the coefficient of lift by a factor that's a function of aspect ratio and span efficiency, and these were discussed in my previous slides. And the equation for induced drag is shown at the bottom here. The trim drag is caused by the downforce of the tail required to balance the moment of the wing lift about the center of gravity. And this was used to find the coefficient of lift of the horizontal tail required for trim. And this affected the induced drag term. The cooling drag was due to necessary cooling ducts because we have a high horsepower motor as well as a large amount of batteries. These batteries are placed here, and here as will be shown in later sections. And these cooling ducts added a certain amount of wetted area to the fuselage, which contributed to the skin friction drag. There are, however, additional drag penalties due to the change in cross-section and the complex profile, but these cannot be easily estimated without CFD or wind tunnel analysis. So all these values were combined into the total drag polar, and this can be used to find the maximum lift-to-drag ratio, which is where an origin ray is tangent to the curve. And this gave us a maximum lift-to-drag ratio of 16.43 and defined our cruise condition. However, you can also use these values to find the maximum endurance parameter and define our loiter condition. These two conditions are also shown in the CL alpha plot here, showing that we cruise at an angle of attack of 4 degrees and we loiter at an angle of attack of 9 degrees, with the corresponding coefficient of lift shown on the right. So in summary, I went over the total drag, which turns out to be 0.0464 at cruise and 0.0809 at loiter, which was made up of the parasitic, induced, trim, and cooling drags, as well as the cruise and loiter angles of attack shown here. And now all these values will be used to evaluate the RFP requirements in the next section by Andy Wilson, which is power requirement analysis.
Thank you, Mark. As a brief overview, I will be talking about the power required, power available, the engine selection, controller selection, power analysis, battery analysis, and the electronic speed controller selection. This is our power required, which is at 6,000 feet, which is our max service ceiling. From this plot, we can find our loiter and our cruise speeds. This plot was created by finding or using the drag from Mark Jaworski section and multiplying it by a range of velocities, which gives us a power required curve. As you can see, we have our loiter speed at 27 knots straight airspeed, and that happens at minimum power, which is at 0.185 horsepower. Our cruise speed occurs when this tangent line from the origin intersects our plot, and this happens at 33 knots straight airspeed at a horsepower of 0.2. Our power available curve, which is this red line here, was found by taking the max power output of our engine, multiplying by our installation losses, and also the propeller efficiencies at multiple propeller efficiencies at varying velocities. From this plot, we can also find our dash speed, which happens when our power available intersects our power required curve. And that happens at 67 knots for airspeed right there. And notice that this black line here is the value that Joshua Parr mentioned earlier from the initial design envelope of 1.16 horsepower. For our engine selection, we selected the E-Flight Power 160 brushless outrunner motor. The max power output is 3.62 horsepower, and after installation losses and the max propeller efficiency, we will see 1.68 horsepower. The propeller selection was originally done on the APC C3 propeller, but that is no longer available from the manufacturer. So we decided to go with, we selected the APC 18x8E. The first number in that series is the diameter of the propeller. The second number is the pitch of the blade, and the E stands for electric. Electric blades are common, they're lighter for electric motors, and they're more suitable for. Our power analysis was done by finding the power required at each flight phase and dividing that by the operating voltage and then multiplying by the time at each flight phase. Notice that our descent and our landing are both zero because we will be performing a power off descent and landing. And our total amp hours will be 24.47. Based on that, we decided to go with, we selected the E-Flight power, or the Thunder Power 5000 milliamp hour 8S25C battery. It is important to note that the batteries are a huge design driver in our design, based on the fact that we need to loiter for 3 hours and then have any other mission time. And our mission time will be later discussed by Chris Sutton in mission performance. For 24.5 amp hours, we will need 5 battery packs, which gives us 25 amp hours. The electronic speed controller selection was based off an engine manufacturer recommendation. They recommended anywhere from 75 to 110 amps, and we selected the Phoenix Edge 120 HP, which operates at 120 amps. So we do meet and exceed that need. In summary, our batteries will be placed around the CG, so we can, that's the heaviest component of our plane, single component, 5 battery packs. And then our ESC will be placed there, and our engine will be placed in the back. These are the propulsion components we decided to go with. And our loiter speed was 27 knots for airspeed, our cruise was 33, and we are predicted both to meet the sustained flight at 30 knots and the 3-hour loiter time. Next, I'll be passing it on to Josh Day for weight balance.
Thank you, Andy. I'll be going over the internal components, the internal and external fuselage structure, as well as the structural weights and the center of gravity, locations, and mass moments for products of the engine. Here are the internal component arrangements for our aircraft. The batteries will be located here and here, as Andy Wilson stated, and that is so that our center of gravity can be at the desired location. The internal component weights were found and then multiplied by 130% installation factor, giving us a total weight for internal components of 20.1 pounds. The external fuselage structure will be made of a 2-ply E-glass, and the weight was found of that being 1.75 pounds. The internal fuselage structure will consist of a floor, ramp, longerons, firewall, and that creates a weight of 1.37 pounds. The fuselage structure is shown here with the longerons, the bulkheads, and the firewall. The structural weights were then found totaling 9.68 pounds. The total weight of the aircraft with all of our components added together was 29.9 pounds, which is just under our weight limit of 30 pounds. Here are the center of gravity locations for our initial design, with the X center of gravity being located at 43.4 inches. Our current design is shown here, with the Z center of gravity locations being here on the left and the X center of gravity locations here. Our X center of gravity is now at 33.4 inches, and our nose gear is located at 7.5 inches and the main gear at 30.9 inches. The mass moments of product of inertia were then found. The I, XY, and IYZ are equal to 0 because our aircraft is symmetrical. And in summary, our total weight is 29.9 pounds, which is just under our required max weight limit of 30 pounds. And our center of gravity is at 33.4 inches. Next, Peter Davidson will present on the static stability.
Thanks, Josh. So for a static stability analysis, I'm going to go over the stability control axis system, our neutral point and static margin calculations, and then our pitch or static stability parameters, pitch, roll, and yaw. This is the axis system we use to analyze our stability control system. You can see that it takes from the center of gravity location, with the X coming out the nose of the aircraft, Y down the right wing, and Z headed straight towards the ground. For the neutral point, we have to take into account the aerodynamic center, the wing body lift, the horizontal tail projection, and the propeller force. I will talk about the horizontal tail projection in a second, because we do have an inverted detail. But we found that to be about 1.5 inches behind the center of gravity, which gives us a static margin of 12% of the mean aerodynamic chord. This is very slightly over our design point of 10%, but it's still stable. It is right where we want to be. Most aircraft are between 10 and 20% for this design area that we're trying to meet. For our pitch stability, that is Cm alpha, that's the prediction per degree of angle of attack. We found our value to be negative 0.6 per radians. Typical value is less than 1.5, so we met our design point there. Roll stability, CL beta, that is Loma reduced degree of side slip. Typical values are between negative 0.28 and negative 0.082 per radians. Ours was slightly outside that range. We came in at negative 0.03. So that could be caused by our lack of dihedral in our wing. We decided to stick without the lack of dihedral though for ease of manufacturability to make sure we can manufacture and keep the costs down. To make up for this, first of all, we're going to further analyze it in internal testing, and when we actually build our flight test article to see if it needs to be designed, and then to compensate for it, if it does, we can use a tighter control law for the control surfaces, and put in better actuators, more precision of our ailerons to account for the lack of roll stability. Yaw stability, Cm beta, that is the yaw movement reduced degree of side slip. Typical values fall between 0.059 per radians and 0.51. Ours came in at 0.113, so towards the lower range of that values, but still falls in there. So we should have sufficient yaw stability. So summary, our static margin came in between 12 and 20%. It's at 12%. Mean aerodynamic chord, we get sufficient pitch stability. It was slightly below our design point for roll stability, but as I mentioned, we should be able to compensate for that and further evaluate it. And we had predicted to have sufficient yaw stability as well. Now I will talk about the control surface sizing. So as an overview, I'll be going over our aileron sizing, our timed bank, and then our inverted V-tail. And that has our rudders, elevators, which are just the projected areas. They're going to form together to form rudder maters. So as an overview for our aileron sizing, we used historical data of the ratio of the horizontal chord and span of current aircraft, and then we determined with that our aileron dimensions should be 0.218 feet in chord and 6.61 feet in span. So you can see there's an image of our aileron sizing right there. Using our static stability parameters that we calculated and a aileron deflection of approximately 20 degrees as recommended by Dr. Bornignon, we came for a time of bank requirement at 60 degrees of bank of 1.3 seconds, which is under the 1.7 seconds that Dr. Bornignon also recommended. This right here is our inverted V-tail. So for our analysis for the Equinox section, we used the projected areas of the inverted V-tail in the horizontal and vertical plane, and then we used conventional equations to analyze that. We realized that there may be certain factors that aren't counted by this, but we can further analyze those using data pulled from our wind tunnel model and our actual flight article. So for the rudders, as I mentioned, these are part of the rudder vaders, but this is the projected area in this plane right here. The rudders control the yaw of the aircraft. We have designed to withstand a crosswind of 10 knots. And with the calculations, we came out to have a chord length of 0.72 feet and a span of 1.05 feet for the rudders. Now for the elevators, using the dimensions of the rudders because they're inherently tied together because, as I mentioned, they're the same surface, the rudder vaders. We came to calculate a angle of attack required for a a deflection required for a 2.5 G maneuver of 10 degrees, and a takeoff maneuver of 8 degrees deflection. So those were having deflections in order to meet those two requirements. So in summary, I went over our aileron dimensions. You can see them right there. Went over our rudder vader dimensions and our rudder vader deflection of plus minus 20 degrees. That is to accomplish our side slip and withstand a 10 knot crosswind. And we are able to also have the appropriate deflection to accomplish a 2.5 G maneuver as well as rotate for takeoff. Next up, Mr. Sullivan will come up and talk about the dynamic stability and control.
Thank you, Peter. This analysis relies on a model provided by Dr. Bordignon, which will take the static stability parameters as inputs and return a linearized model of the aircraft. This analysis was performed at cruise condition for our aircraft. And based on, the idea is we already know from Peter Davidson's section of static stability control that the aircraft is statically stable. This will tell us what will happen when it's disturbed away from that stable condition. For the goal of our project, we'd like to have positive dynamic stability for all parameters, but we find out that's not quite met, but it's very close. It's broken into two major sections. We have the longitudinal mode, which deals with pitch. In this, there is short period mode and fugoid mode, where short period is related to the pilot input, and fugoid is related to aircraft parameters and the imbalance of small imbalance of forces on the aircraft. The second set is the lateral directional mode, which is related to the roll and yaw. The first of these is the roll mode, which tells the resistance of the aircraft to rolling. The second is spiral mode, which is it's an interface between the roll and yaw, and they will add onto each other and eventually take an aircraft that was slightly out of a stable condition and roll it into a spiral that is going down very quickly. The third is the deathfall mode, which has the potential to rock the aircraft too much for our gimbal to actually keep track of the target. Our poles and zeros that were generated from the model show that all parameters are stable except for the spiral mode, which is very slightly unstable. It has a time to double of about 6 seconds, which is acceptable for our aircraft. This plot shows where the acceptable ranges are, which everything in the white is acceptable. Black is beyond what the best control systems we have now can do. Red is the state of the art. Yellow is beyond the scope of this class. As I said a second ago, everything in the white is acceptable. These poles are all at either have a damping ratio of either 1 or above 1. These two are the spiral mode, which has 1 at 0 and 1 at a damping ratio of -1, but its frequency is low enough that it's acceptable for our purposes. In summary, we meet the dynamic stability control requirements. The only thing that is not stable is the spiral mode. This has a time to double again of almost 6 seconds, which is beyond our minimum requirement of 0.25 seconds. Now I'll hand this off to Lori Conklin for structures.
For structures, I'll be going over the wing, empennage, landing gear, and fuselage. Our materials, the wing and empennage will both be 2-ply carbon fiber. The landing gear will be 36 plies carbon fiber. And then Josh Uday discussed the fuselage will be in the weight balance section. Our wing currently uses the Epler E67 airfoil. This will be further reevaluated in detail design with aerodynamic analysis. Our aspect ratio will help us meet our high range and endurance requirements for the RFP. And our planform area of 15.4 will be used to meet the requirements that Joshua Parr laid out in the initial design envelope. The internal structure of the wing is currently 2 spars with 48 ribs. This will be further reevaluated in detail design as well. We have 2 disassembly locations, here and right here. And this will allow us to meet our disassembly requirements for the RFP, which will be further discussed by Paul King in the support section. We are utilizing a twin boom inverted V-tail. This will help reduce the interference that the tail sees from our push propeller. Our tail cord is 1 foot. This will allow us to meet control surface sizing requirements. And our current airfoil is NACA 0012. This will also need further analysis in detail design. The internal structure of the empennage uses 1 spar, at 22% chord, and 5 rips, 2 at the apex for a total of 10 for Professor Helbling's recommendations. Our landing gear utilizes Roscom's 15-degree tip bag and 55-degree tip over assumptions, and then our tip bag is actually 18 degrees, so it reduces the chance of prop or tail strike. Our main gear will take 85% of the weight, and our nose will take 15%. Our critical loading value is 100 pounds, as shown in this ANSYS analysis. We use the 100 pounds on one strut to give us a conservative structural analysis estimate. The 88.6 KSI is our max principal stress, and that will be at the attach point of the gear, the main gear. We are using a leaf spring nose gear design to reduce the blockage that the payload will see so that we can get our mission completed. Our fuselage, originally the CDR was a cylindrical fuselage, and it's now been refined to include a nose cone and taper at the aft end of the fuselage. In summary, these are our total weights. We are currently predicted to meet our weight requirement, and the individual components are currently predicted to meet our weight requirements. Again, structural and internal testing will be done detailed design. And now Christopher Stephan will discuss our mission profile.
Our mission begins with takeoff at an altitude of 5,000 feet MSL, transitions to climb to 1,000 feet AGL, and cruise out to loiter location. Loiter for 3 hours while observing our targets. Cruise back, descend, and landing. Our takeoff is found from this equation, and we have a takeoff ground roll of 80 feet, which will take us about 3.5 seconds to cover. We'll take off from an asphalt runway as is designed for the smart transportation, which will have asphalt available to them. Our climb is found to have a rate of climb of 20.7 feet per second. We reach an altitude of 1,000 feet, as I said a second ago. It'll take us 48.3 seconds and cover a distance of 1,680 feet to reach that altitude. We have 2 cruise sections. The first cruise out will take us 20.8 minutes and cover a distance of 9.7 nautical miles. The second is cruise back, which will take 15.4 minutes and cover 7.2 nautical miles. The reason for the disparity is due to the increase in distance for descent when compared to the climb. Our loiter will follow this pattern, this is a grid pattern, with a 5% overlap on each end of each side of the swap. We'll cover a distance of 80 nautical miles and an area of 8.71 square nautical miles when it's set to a recognized vehicle. Our descent will take 8.0 minutes and cover 2.78 nautical miles with a sink rate of 2.4 feet per second. The landing ground roll is found from this equation to be 620 feet and take 24.9 seconds. There's no RFP requirement for the landing ground roll, but we set ourselves a goal of 300 feet, as this corresponds with the takeoff ground roll of 300 feet as required by the RFP. We do not meet this, however, by using our ailerons as spoilers, we should be able to get fairly close. And there may be small design modifications, such as using our elevators or reservators to increase drag as well. In summary, we meet all RFP requirements. The only thing we do not meet is our own goal of a 300-foot ground roll. It will take us 3 hours and 45 minutes and cover a distance of 100 nautical miles for the mission. And Morgan Conklin will present the control element.
For control, I'll be discussing the ground and flight control system as well as security for our UAV. This is our ground control station. It will help us meet our RFP requirement for out-of-sight and line-of-sight transmission. We will be utilizing a simple laptop to bring together our video feed from our payload as well as our software used for our autopilot. It does meet the autopilot, the RGPilot autopilot software requirements. This is an example of the autopilot software. It's simple to use, and there's plenty of waypoints, so we're not in danger of running out of waypoints. This is our flight control system. It's a simple RC controller, which will help us reduce any training time for crew. And it can be used for visual range, and then we'll switch to autopilot for out range. For security, we'll use data encryption, user authentication, and secure network interfaces per suggestions in Gunlock. In summary, these are our flight and ground control systems. And now Paul can be discussing support.
Thank you, Morgan. So today I'll be talking about the reliability, the maintainability, the spare parts, and how this thing will be transported. So the reliability, Based on Austin's assumptions of the structural lifetime, the durability lifetime was predicted to be 5,000 flight hours, and the autopilot battery lifetime is 2,500 flight hours. This is the mean time between failure and the reliability calculations. Austin provided a range of mean time between failures for the components, and we took an average of that range and calculated the percent reliability shown above. Maintainability, this is spare parts list. Key things to note is that there will be a complete set of transmitter antenna that could replace either communication systems on our aircraft, and that can be changed on frequency based on software installation. Also, there will be a full battery set that will be spared, and that could help reduce the downtime if back-to-back missions are decided to happen. Transportation, the RFP requires that the Sting has to be disassembled and transported in a 3-foot by 3-foot by 6-foot box, and this box has a 1.5-inch padding that's implemented on all dimensions. There will be a separate box that contains a spare parts container, as well as a toolbox, and all these boxes will be transported in an open bed truck. So this is a CAD drafting of disassembled Sting location. Things to take into consideration is that the transport container was designed as a frame to show the internal components as well as show the 1.5-inch padding implemented. Also, the Sting is disassembled in five parts. The V-tail will be connected with the boom, but will be disassembled from the wing, and the wing will be disassembled at the fuselage, the mid-wing section, and the wingtip sections. And also, the landing gears will remain intact with the fuselage to reduce the assembly and disassemble time for the Sting. So in summary, the durability lifetime of our aircraft is 5,000 flight hours based on structural lifetime, and we have the desired spare parts for our aircraft, and the Sting and disassembly will fit into the transport container. And next I'll hand it to Christina O'Keefe to talk about the cost and risk analysis of the Sting design.
So for the cost and risk analysis, I will be going over the overall price of products, research, testing, design, and evaluation, the unit flyaway cost, and method comparison, and then the risk analysis. These are the overall prices of the components. As you can see, the payload is going to be the most expensive at $90,000, but this is the mission driver, so we want a better product. For the research, testing, design, and evaluation, we use the overall cumulative hours for this semester and then hours from a previous detail group and multiply them by cost per hour, including overhead, and come out with a cost of just over $260,000. This includes the wind tunnel test model, which came out to be $298.60, and then a budget of $2,000 for the flight test article. For the method comparison, we had cost estimating relations derived from Gunlock and Raymer, and these include the cost of the spare parts, as mentioned in the support section, along with the cost of 100 units. The average came out to be just over $22 million. For the cost of operations, this is based on the spare parts and the mean time between failure that was mentioned by Paul Kim in the support section. The autopilot is the only component that will need to be replaced twice, so the cost came out to be $750 for the autopilot throughout 5,000 flight hours. For the overall cost of the operations, it came out to be just over $2,500. In summary, the research, testing, design, and evaluation for one prototype is just over $260,000. The average cost for 100 units is just over $22 million, including spare parts. The operation cost for 100 units is just over $250,000, and a single unit of the Sting will be just over $220,000. After the analysis of all of the components that have been previously mentioned, we were able to put together a 3D model and print it, as you can see here, and then we will go on to testing and the detailed design. Mark Tversky will go over the wind tunnel model fabrication that we will put into next semester.
Thanks, Christy. So I'll talk to you about how we put together our wind tunnel model for wind tunnel testing. So once the preliminary design was finalized, our job was to develop a wind tunnel model that could withstand 40 pounds of lift load, and could withstand the other wind tunnel testing forces. The goal for our team is a complete model, all manufactured and assembled by the start of next semester, so that we can get right into structural wind tunnel flight testing during the detailed design phase. So here you can see the configuration of our wind tunnel model. We have 5 3D printed parts: the nose cone, the fuselage and root section, which is a fused component, the 2 outer wing sections, and the V-tail. All these will be connected with a steel substructure and mounted on the platform balance, as seen here. 2 considerations to note here is that the wings got exceedingly thin, and the printer would not allow for them to be that thin, so we had to add some reinforcement right here at the boom locations and at the V-tail locations. Now this will add a small amount of drag, but we think that it will be necessary because we want a conservative estimate for the drag during wind tunnel tests. The steel substructure is shown here, and we have 2 tail booms, which will be 1/4-inch steel rods and have slots cut into them, as shown here, so that they can transfer the tail load to the spars without transferring loads through the plastic parts. And the centerpiece will be epoxied through the center of the fuselage, and it will hold the spars. And the centerpiece will also be bolted to the platform mount. Thereby, we don't have any large loads traveling through thin plastic components. Here's a drawing of our wind tunnel model. It will have a scaling factor of 1 to 5.039, and just over 35 inches in wingspan, just over 16 inches in length, and just over 6 inches in height. The platform area, which is at 87.5 inches squared, will be used to calculate the Q limit of the wind tunnel, or the speed at which we should run our wind tunnel tests. And it will not block more than 5% of the wind tunnel area at a maximum angle of attack of 14 degrees. Here's the parts list. Note that our landing gear will have an epoxy nut into the fuselage, and the main landing gear will bolt directly to the centerpiece, so they can be removable in case that their drag component or drag contributions are not realistic. Also, our wings will be wrapped with carbon fiber to add stiffness on the top and the bottom with unidirectional carbon fiber, and that will also reduce the flexure during wind tunnel testing. Here you can see how the parts come together. Note that the tail can come on last after the spars are already inside the fuselage and wing, and this will allow us to do tail off as well as tail on testing. Also, as I said, the landing gear will be removable, and the wings will be reinforced with carbon fiber sheets. So in summary, our model, as you can see on the left here, is made out of 3D printed ABS plastic with a steel substructure, and the tail can also be attached after most of the body has been put together to do tail off and on testing. Our landing gear will be removable, our wings will be reinforced, and it will not cause a significant amount of blockage. Next, Claire Cluster will talk about our project management.
So we'll go over our cumulative labor hours to date, and then our hour breakdown, as well as predicted versus actual labor hours, and then wind tunnel model costs. So here are our hours to date. We have roughly 2,383 hours. This is broken down into engineering management, engineering, technical, administrative, and professional development. With the bulk of our hours being professional development, which is class time and individual research. So here's the breakdown of our hours. Like I said, professional development has the majority of our hours, with administrative coming in next. Professional development is class time and research individually. Administrative is editing documents and writing papers. And then technical is CATIA work, along with engineering, which is Excel sheets and drafting, and then engineering management being team meetings. So predicted versus actual, the predicted hours were provided by Professor Helbling, which was given by last semester's detail. We are slightly under the predicted because this was given by the detail team. Our hours for detail will be different than our hours for now, considering detail has manufacturing for the actual aircraft. Here's our wind tunnel model. As Christy had gone over in the cost analysis, it was roughly $298. This was $3 per cubic inch for printing. And I'll go over preliminary conclusions and recommendations for the team. So here's a summary of our design. As we said, the payload runs the mission, and then we have the ailerons, our inverted V-tail with the carbon fiber booms, and then pusher top. Here are the requirements evaluation table. Again, on the left is the RFP requirements. In the middle is where we stand today, and then on the right is if we are to be predicted to be met. The only one that we are unsure about is the recovery and assembly of 20 minutes, which will be evaluated in detail once the flight article is constructed. Limitations and recommendations. So we're limited to the ability to calculate certain values, such as Oswald efficiency, and so this will be done during testing in the detail phase. And then limited historical data for the SUAS. This can also be done during wind tunnel testing. And then wind tunnel model and the flight test article do differ, as Mark had gone over. As you can see here, we do not have this extra part in the front, but to account for this, we will add drag, which will give us a conservative estimate for our flight conservative. Future tasks will be completing our wind tunnel test plan, and then we'll move into standing the wind tunnel model, and then carbon fiber wrapping the wings, and then machining our non-printed parts, such as the mount, and then we'll move on to detail design, which will be wind tunnel testing in the fall, and then flight testing. So acknowledgements, we'd like to thank Professor Helding, Dr. Bett, our TA Garrison Robertson, Dr. Bordendon, Dr. Trout, Andrew Brandt, the RC champion, and then Mr. AJ Olson, Mr. Steve Jacobson, and Mr. Ed Brandt. Thank you. Here are our references. Now we'll look up questions.
Very nice. Can you guys hear me? Very nice presentation. Clearly very well organized and rehearsed. 175 charts in 1 hour is pretty impressive. Like your design. Like the vehicle, and it's clear that you guys have put a lot of effort. You should be proud of what you've done. Wanted to get to some of the requirements. You have, I think it's an inferred requirement or a derived requirement for a gimbal sensor. I didn't see that in the actual requirements that were listed here. And it seems like that's probably the most expensive part of your vehicle. If this were the real world, you could go back to your customer potentially and clarify that requirement, because it sounds like what you're going to be doing basically is flying along a known route. You've got vehicles, your cruise speed is less than, say, traffic. So you may not need the gimbal requirement for this vehicle, and that may be trumped by be cost effective to allow 100 units. So you might want to consider that for this activity and for future work as well. Also, your pedostatic probe has it looks like an alpha beta capability, and for this particular vehicle, I would think you wouldn't need that, and that may be adding unnecessary cost to your alpha beta or your pedostatic probe. So you may consider that. It looks like I'm not an expert in propulsion, but it looks like you may be underpowered for a 30-pound vehicle. But maybe Ed has more insight into that than I do. For considerations of maneuverability, for getting yourself out of trouble, and just pilot handling. But I know your calculations are showing that, but that may just be something to think about. From a vehicle fabrication perspective, I have some concerns about looking at your weights. It looks like the internal stuff is most of the vehicle, and you leave about 6 pounds for structure, including landing gear. So you may run into a durability and a handling issue, especially if you're looking at using this airframe for 5,000 hours. 2 layers of carbon. You might want to consider tool droppage onto the vehicle itself. Just a general handling of the vehicle. If you got rid of that sensor, you may be able to buy yourself some weight back in order to add a little more thickness and durability to your external aerostructure for a 5,000-hour vehicle. I really liked the way that you guys handled the stability control issues. This has a ArduPilot on board, so you can take care of the unstable spiral mode and some of your yapping issues with some feedback control. I think that was, you guys did a good job of explaining that, and I think that yeah, in general, the kids did a great job of putting this together. One other question I had was, how did you come up with a 40-pound requirement for the wind tunnel testing? It seems like that, given the 30-pound vehicle, that's about 1.3 Gs, that might not be quite enough. So
That was part of the wind tunnel capabilities. The balance can take 50-pound load. So with a factor of safety on that, we had a 40-pound load maximum.
Okay, great. So, can you guys address the sensor issue? If I think somebody might have a comment.
So for the payload, we are barely right now meeting the requirement to be able to identify the license plate. Being able to read is a very complicated task. So the idea behind the gimbal system, from our perspective, was the plane's going to be pitching and rolling in the air and stuff. So we wanted to be able to make sure you identify the license plate at all time and then be able to track that target. Or, for example, if you're patrolling around an intersection or something as well, be able to lock on there. Now, we could further evaluate that to see if it actually is necessary, as mentioned. But from our perspective, we just thought it'd be better to account for that now, rather than surprise a customer per se and say, oh, just kidding, we need another $90,000 for a gimbal system, and drop that to the customer at the last second. So, yeah, it warrants further evaluation. Thank you.
Nice work.
Great job. I think you covered a lot of the bases that I don't normally see, and so good job on that. Particularly, I'm thinking of having actually shown me where the gear is, why you have the numbers you do. Concur with the alpha beta comment. You're putting a lot of money into your alpha probe. All you really care about is executing altitude. So save some money there. You showed that your comm system is good for price requirement. It's probably too much money. You can back off there. Cost is a big driver. On the other hand, Oswald efficiency factor 0.93 and most really flat plane. That may be optimistic. And when you were talking about the batteries, I kind of mentally thought, well, maybe there's a better way than having internal cooling, like having the batteries in the airstream or aligned on the side of the airstream, something of that nature. S&C. Did the ailerons look like they may be a little large for what your gut check would be?
These are just based on calculations that we ran. So that's something we could further evaluate in our flight test article. That's just based on our preliminary calculations.
The historic data you used?
Yes.
Great. Now think about the history of the historic data.
Yeah.
All manned aircraft. Yeah, you can't trust, I know Dr. Boylan gave that to you. But who did he get it from?
Probably a loser.
Yeah. So when I was putting that together, that's all airplane. And inertia doesn't scale at the same rate as mass. So just when you do that type of thing, look at, okay, how can I adapt the data I have to better fit my system?
Absolutely.
But I'm glad you did use historic data. I'm glad you looked at stability control the way you did. It's a very good job on that. Time to double 6 seconds doesn't scare me at all. So. And then talked about failure mode, failure analysis. You said, well, we'll probably have to replace the autopilot twice during the life of the vehicle. If the autopilot fails, do I get the plane back? Just something to think about.
We considered if the autopilot did go off, that hopefully it would be visual range, but we haven't considered if it was outside visual range and the autopilot did go off.
And so you have MTBF, which is great, but there's also this whole family of other MTs, like mean time between critical failure, and those go into driving probability of loss of aircraft, probability of loss of control, a few other things. So you definitely went down the right path, probably as far as anybody has ever seen go that way. But great job on that. And then the other was just manufacturing. Can you get cost out of the vehicle by looking at maybe foam as opposed to a real aircraft structure?
We have briefly talked about this with the wing. Maybe instead of having 48 rooms during detail, we can fill it with foam and eliminate some of those rooms and add some material structure to that.
And with the trade wing, I think that's the right thing to do when you get there. So, great job.
Reiterate that we were working with a lot of information. I saw some things too.
You got it, AJ.
I saw some of the things that I haven't typically seen out of some of the presentations as well, so that's appreciated. On the presentation topic, I've got one yet. Please give us Stroud for capitalization investment. Beware. On the sensor topic, talked about reading a license plate a lot. What are the standoff distances and what are your expected loiter radius, and can your chosen sensor actually use the license plate?
So our chosen sensor, for electro-optical, that's one of the identification. It can go down to about 1 degree field of view with the lens, but the reason why we chose that system, it's interchangeable. So for some reason, because right now we're just predicted to do that, and if we can't actually do that, we can always swap up to a more expensive camera system or a more expensive lens. The system is able to take on any Sony Block EO camera, and I'm sure it would be able to modify it as well to take on any camera we need. That just straps our cost up. Now for the actual mission performance section, did you cover this performance? Yeah.
So my analysis for the area covered was just using a grid pattern. So I'm not as familiar with the specifics of how much like the radius you can go with, because I was using a predetermined swap width and basing it on that. So
yeah, that's one of the perspectives where just to make sure that you've got this requirement, so the different disciplines need to make sure that they're in lockstep, so that your air vehicle does its job, but it also provides the sensor its capability or ability to do what it needs to do as well. So you talked about swapping the sensor now, you did plates into one of the other questions. I didn't see a CG range when we considered weight balance. It was a single value. So if you swap a sensor or you have an ability to fly a vehicle partial mission capable, your CG is not going to end up in the same spot. What are your bounds for 4.5 limits?
Our plan on that is if the CG were to vary, we have the batteries being able to move so we can reposition the center of gravity at our desired location.
Okay. So you don't actually have established 4.5 bounds. Okay. One last question for you. What were the design loads for sizing the structure and where did they come from?
Do you mean on the actual airframe or the landing gear?
Both. It's all part of the air vehicle structure. I saw one value in there during the landing gear spot. I think it's at 100 pounds, but I didn't see any reference to any numbers for the rest of the structure, at least preliminary sizing.
So the landing gear uses a critical loading equation, and in that equation is the value from CFR 23 that states it's a 2.67 for a normal aircraft, and since there's not much data on a UAS system, we went with that value and then calculated the critical loading and used that with the 215-degree guidelines as well as the 55-degree guideline in order to determine the spacing of the landing gear. So that's the landing gear part.
We haven't actually structural tested the wing structure in ANSYS yet, but we will be doing that in detailed design and modifying the design based on what we get from that.
Okay, you still have to have a load to apply. So your comment about using Part 23 is actually really great guidance. So when you look at the airframe on the whole, go back to Part 23 and start. Good work, guys.
Okay,